Hello everyone, for this tutorial video I would like to explain the derivatives of the 6 trig functions, as well as give comprehensive explanations of the special limits that will appear in the proofs. If we first attempt to take the derivative of the sine function using the literal definition of the derivative, we see that unfortunately we cannot simplify it using the traditional laws of algebra. But what we can do is use a formula of sine of a plus b equals sine of a times cosine of b plus sine of b times cosine of a, which we will have to prove first before we can apply it. So if we examine a diagram such as this, we see from basic trigonometry that the sine of a plus b is the ratio of from p to q over o to p. But we also see from p to q is from p to t plus t to q. So now we can break this up as two separate fractions. And we also see the measure from t to q is congruent and therefore exactly equal to the measure from r to s. So now we perform a more tricky algebraic maneuver, where we multiply and divide the numerator and denominators of the two separate fractions by common factors, which might seem to make things unnecessarily complicated. But if we look closely at the diagram, we should be able to conclude our final answer. Namely, that from p to t over p to r is the cosine of the angle between these. From p to r over o to p is the sine of angle b. From r to s over o to r is the sine of angle a. And from o to r over o to p is the cosine of angle b. Lastly, we see the first angle is congruent and therefore equal to angle a. So our proof is complete that the sine of a plus b is exactly equal to the sine of a times cosine of b plus the sine of b times cosine of a. So now we plug this in and attempt to simplify the fraction as much as possible using traditional algebra techniques. But we are stuck again because we have two limits that cannot be simplified algebraically, namely the limit of sine of h over h as h approaches 0, and the limit of cosine of h minus 1 over h as h approaches 0. However, we can prove these limits using trigonometry as well as some calculus techniques such as the squeeze theorem, which we will do now. In particular, we would start with the unit circle, or the circle of radius 1, to make our work simpler, and then draw two similar right triangles that both meet at the same point, but whose lengths are different compared to each other. So now we should be able to see that the sine of x is the length from b to c over the radius of the circle, or from b to c over 1. And we next see the tangent of x equals the length from d to e over 1. So we next draw a scalene triangle whose area should be defined as 1 times the absolute value of sine of x over 2. From looking at the picture and considering what the length and height of the triangle must logically be. We next fill in the curved portion next to the triangle that is inside the circle as well, and attempt to ask ourselves how we can find the area exactly. We know already, since the unit circle has a length of 1, its area must be pi. And if we next take the arc length that includes the triangle and is not simply just that shaded region, we should be able to logically guess that the area is x degrees divided by 2 pi. So now we multiply this by the area of the unit circle and conclude that the area is x over 2. And we next figure out the area of the larger triangle, which we can see is 1/2 times base times height, like for any triangle. And we see the length from a to d and the length from d to e would both constitute these legs. We know the length from a to d is congruent to the radius, which has a measure of 1. And the length from d to e was derived earlier in the proof, which is absolute value of tangent of x. So the area of the entire triangle is absolute value of tangent of x over 2. So now we can see by visual estimation, the smaller triangle has a smaller area than the arc inside the circle, and the arc inside the circle has a smaller area than the triangle that goes beyond the circle. So we use less than or equal to signs to compare these areas like so. We next multiply everything by 2 to make the inequality simpler to compare. We rewrite tangent as sine over cosine by the trig definition. And we next divide everything by the absolute value of sine of x to get it more readily in terms of the limit we are trying to find. So now if we take the reciprocal, or 1 over the fraction, the comparison would be in reverse to what it normally was. And next see, in the context of this problem, sine of x and cosine of x are positive, so we can drop the absolute bars to simplify our work. So now, as we take the limit as x approaches 0 for this inequality, we see 1, as it is a constant, is obviously not affected by x and remains 1, but the limit as cosine approaches 0 is also 1. So therefore, the limit of sine of x over x equals 1. There's a very good reason we did this proof first, because the proof of cosine of h minus 1 over h as h approaches 0 will actually involve this very proof, as we will see. In particular, we would start with the limit asked, but then multiply the numerator and denominator both by cosine of h plus 1. So the numerator would be cosine squared of h minus 1, which with some clever rearranging can be thought of as the negative of 1 minus cosine squared, which we know is sine squared by the Pythagorean identity. So now we factor it as negative sine of h over h times sine of h over cosine of h plus 1. And we see, because we have a limit of 0 times the limit of something else, the total limit is 0. It doesn't matter what the other limit is. So now that we have proved exhaustively these two special limits, we would simply plug in their numerical values and the derivative of the sine, and we should be able to conclude that the derivative of sine is exactly equal to cosine. To prove the derivative of cosine of x, we would use another trig formula, but this time the cosine of a plus b instead of the sine. We see the cosine of a plus b is the ratio of these two sides, which is the difference between a larger leg and a smaller leg, so we break it up like so. See, the length from b to d is congruent and therefore equal to the length from a to c. Multiply and divide the numerator and denominator in the two separate fractions by common terms, and look at the graphic again to determine what these ratios are the cosine and sine of. And lastly, note that angle EAC is congruent to angle alpha, so we conclude the cosine of a plus b equals cosine of a times cosine of b minus sine of a times sine of b. So now we plug this into the cosine derivative formula, simplify it using techniques from algebra, and plug in the special limits we proved for sine of x where appropriate. We should be able to conclude that the derivative of cosine is negative 1 times sine. Since we know from trigonometry the tangent, cotangent, secant, and cosecant are all defined as ratios of sine or cosine, we'd simply use these definitions and the quotient rule in order to compute the derivatives. Once we do the work, we get the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared, the derivative of secant is tangent times secant, and lastly, the derivative of cosecant is negative cotangent times cosecant. Now that I've explained thoroughly how to find the derivatives of all 6 trig functions, we can move on to the derivatives of exponential functions, logarithmic functions, and inverse functions in general in the next video, as logarithmic functions are specifically defined as inverses of exponential functions. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.